So when we look out into space, we detect the light of distant objects, galaxies, nebulae, star clusters, stars themselves, planets, whatever. But the problem is that we generally have to look through the Earth's atmosphere. I mean, when you look up, there's like 50 miles or so of air above you, give or take. And so you have to look through all that air, and that air affects the view. So as the light passes through the air, it actually affects the light and changes what you're looking at. The first thing we'll talk about is atmospheric extinction. What happens is that as the light passes through the atmosphere, then it scatters some of the light. The blue light is scattered more than the red light. So remember that the spectrum, red, orange, yellow, green, blue, indigo, violet. So if we scatter those colors right there, then if you're going through a lot of air, then what's left is the red, orange, yellow colors. Now, if the light's coming straight down on you, you're going through less air, and so there's less scattering. But if you're looking at something rising or setting, then you're looking through a whole lot more air. So that's going to get rid of those shorter wavelengths, and what you're going to see is something that looks redder. Now, everyone's gone out and they looked and they've seen the sun rising or setting, and it looks reddish. Two things are happening here. One, you're scattering, getting rid of some of the light, but you're also absorbing some of the light. So it actually looks dimmer. One of the labs that you do is actually go out and watch the sun rise and set. And one of the things you notice is, well, the sun is like blinding bright when you look up straight up in the sky at it, but it's not nearly as blinding bright when you look at it on the horizon. And that's because there's atmospheric extinction. So the atmospheric extinction is not just extinction, it's also atmospheric reddening. So we are making it redder. It's dimmer and redder. Well, it's not just the sun. I could replace this with the moon. A lot of people, when they're going out and they're looking at the moon, they'll come back and tell me, wow, I saw the moon rising tonight, and it was a big red thing. Why is that? Well, the same reason the sun rising is red. You have this effect. Now, obviously, the more stuff that's in the atmosphere, the bigger the effect is going to be. So more pollution and so forth actually makes for prettier moonrises and moonsets and sunrises and sunsets. But it's annoying for astronomers because it does the same thing to stars. Stars have colors, but you're now making them redder and dimmer when they're near the horizon. It's much more difficult to get precise measurements of stars when they're near the horizon than they are when they're high in the sky. So astronomers would calculate when are things highest in the sky, and that's the best time to go observe them. And so that's the effect of the atmosphere. It's one of the effects of the atmosphere. And if you're doing this professionally, you have to take into account this effect, subtract it back off. Well, the effect is different for different colors of light. It turns out for certain wavelengths of light, the atmosphere is just plain opaque. X-rays don't even pass very far through the atmosphere. They pass feet through the atmosphere. So you go get an X-ray somewhere, and the technician will step outside the room. They don't necessarily have to step behind a lead shield. They just step outside the room, and that protects them because the X-rays only go so far. 12 feet of air can block X-rays like a millimeter of lead. And so they put lead over you, and they just let air block them. Well, things give off X-rays in space, but you can't see those X-rays because they don't pass through the 50 miles of air. Likewise, most ultraviolet light is blocked by the atmosphere. The ozone in the upper atmosphere blocks most of the ultraviolet light. Water vapor in the atmosphere blocks most of the infrared. Now, most of that water vapor is in the lowest levels of the atmosphere. And so what you do to get above those lowest levels is you may go up to the top of a mountain somewhere, and then you get to see in the infrared and see things that don't make it all the way to the ground. Most of the radio waves make it to the ground, but at really, really long wavelengths or really, really short wavelengths, like some of the microwaves, don't make it much through the air. And so the wavelengths that do make it all the way to the ground, we call atmospheric windows. So this is the range or the bands of electromagnetic radiation that make it all the way to the ground. Now, one of the things about the infrared light is the atmospheric window actually extends down to the stratosphere, but not much below that. And so that means that the higher you are in the atmosphere, the better you see infrared. So that's why a lot of observatories are on top of mountains. And actually, it's not the only reason. There's less other atmosphere up there too. And so all those other effects, the reddening and the dimming and the extinction, all that is lessened by being on top of the mountain. And it's really your only hope of finding, for example, infrared telescopes. This picture right here is actually of Mauna Kea Observatory in Hawaii. And that white stuff in the picture is snow. This is such a high elevation here that it's always cold, typically below freezing. And so people don't normally think about Hawaii as being cold, but up at the top of the mountain, it is. Now, the other thing that happens is as light passes through the atmosphere, that the atmosphere moves. It's got turbulence in it, and that distorts the view. And so here is an image of a crater on the moon that's distorted by light passing through the atmosphere. And so this is actually like a little video here clip of how this is happening. And so obviously you do a time exposure of that and it all blurs the whole thing out. Now, you know this happens. Summertime in Texas, you go out there and you're driving down the highway and the sun heats the ground, the air is rising in front of you, and everything's shimmering. And so it distorts it. So this is atmospheric distortion, what we'll call seeing conditions. Perfect seeing conditions means the atmosphere is not moving very much and everything looks crystal clear. Turbulent air, poor seeing conditions means things are dancing around. And you can go out at night and look on good seeing conditions. The stars look like little pinpoints in the sky. On bad seeing conditions, they look like they're kind of dancing around a little bit. Layman's term for that is twinkling. In particular, but what happens is different colors are distorted differently, and so I sometimes, on poor seeing conditions, can look at a star and it looks like it's twinkling different colors because the different colors of light are bouncing around differently. Now, obviously, this messes up what we're trying to do with measurements of this. So there are ways of dealing with that, but it is a problem. Radio telescopes have much less of an issue here with the atmosphere. The radio wavelengths go through the atmosphere much better normally, so radio telescopes can be located pretty much anywhere as long as there's not other radio signals. Ultimately, though, the atmosphere, to get rid of the atmospheric effects, you have to get into space. And so you use space-based telescopes. The Hubble telescope is what in the media is often called the space telescope, but it's really a space telescope. There are lots of space telescopes that are up there. And so it turns out the Hubble happens to have, is one of the biggest and most expensive and has the best press office, but there are plenty of other space-based telescopes that don't have to look through the Earth's atmosphere. The Hubble uses a lot of visual light. A lot of these others are specifically set to be X-ray or infrared or gamma rays or something that don't pass through the atmosphere very well. And so that's why they're up there. There are distortions with visual light too, and the Hubble can do it all. But well, not all, but it does a little bit of infrared and ultraviolet and visual.